Hello students, today I am going to discuss on microcontroller lab experiment number 4 Boolean and logical instructions. Myself I am Chetan, assistant professor EC department at SMVITM. So I have got here 4 tasks. We have 4 tasks to do. So writing a program to perform logical operation. So we have to check and validate how the AND operation can be done, OR operation can be done. Similarly, XOR, then NOT operation can also be seen. So in the second task, we have to find out the number of ones present and zeros present in a given 8-bit data or 1 byte data. The third task we have here is write a program to reverse a given data. The fourth one, we have to find out the given data is palindrome or not. So this program is related to the reversing a number, then finding out whether the given data is palindrome or not. So the four tasks what we have to understand the Boolean and logical instructions. Let's move to the first one. So in order to perform the logical operations, we should first understand what are the syntaxes or how many instructions available in the logical instruction category. So for AND operation, we have ANL. AN stands for AND, L stands for logic, AND logic. And this is the syntax, destination and source. Similarly, for OR, complement logic, this is for NOT operation, this is for XOR operation, X or L, destination comma source. For rotate operation, we have the 4 instructions here. RL stands for rotate left accumulator, RLC stands for rotate left through carry accumulator, rotate right accumulator, rotate right through carry accumulator, and this is swap instruction, swap A. So continuing the logical instruction format or syntax, so mostly the destination should be accumulator and the source can be any of the addressing modes like register addressing mode or direct address location, direct addressing mode, immediate addressing mode, indirect addressing mode, or any of these formats you can use. So these are the permitted formats to use OR operation, XOR as well as AND operation. Let's try to understand the first program to perform a simple logical operation AND or XOR. So I have already written instructions here, as well as I have assumed some data which is available in the respective location, and when I use this instruction, immediately it gives a certain result. That result must be moved to the respective location like 32, 33, 34. So the data is available in the 20 and 21 consecutive locations, and the result must be stored. And result should be stored in the 32 location, or result should be stored in the 33 location. 34 location must comprising of XOR result. So for that, I am moving the content of the 20H to the accumulator and using this instruction perform AND operation with the accumulator. Accumulator is holding FFH, 21H holding this second data 0FH. When you look at this, so it's AND operation, we know the truth table of AND operation. Whenever we have both number of 1, so when it is multiplied with the dot operator, so we will get as a result it will be 1. When it is multiplied with the 0, as a result it will be 0 here. So dot operator reflects a multiplication operation. So in this way we are getting the result 0FH, which is moved to the 32. So this first 3 instructions serve to perform, to find out the first AND operation here. The next 3 instructions you can see for OR operation. Again the data is assumed in the respective location 21, 20 and 21, and the result what we get is 1, 1, 1, 1, series of 1 or 8 1. So that is FFH equivalent, which is stored in the 33H location. So for the next 3 for XOR operation, you know the truth table. Accordingly, we are getting F0 result, and this is moved to the 34H respective location. So this is how we can analyze the first program to perform a basic logical operation. So in addition to this, if I want to perform a NOT operation, we have an instruction of like CCL, complement logic accumulator. So here some data is assumed, 55 is moved to the accumulator. Now when I complement this, so as a result it becomes AA. So 0 is replaced by 1, 1 is replaced by 0. So this is how we are getting a AA after using this instruction. Let's move to the second task to find out the number of ones and zeros present in a 8-bit given data. So in order to understand that program, so we have to go for understanding the rotate instruction. So the first rotate right accumulator instruction, if you explore, so the syntax, how it works is given here, logical syntax. So the LSB bit moves to the most significant bit. And here some example being illustrated here. When 36 immediate data is moved to the accumulator and binary representation is this. So when I use the first only once RRA, so the data becomes in the accumulator like this. The LSB data moves to the MSB. Similarly, this shifts one place, this shifts one place, likewise it continues. So this data shifts here. Similarly, a series of rotate instruction if I use continuously for the same accumulated data will be contemplated. So this is how your rotate right accumulator instruction works. Similarly, rotate left, your MSB moves to the LSB. Example being illustrated here can be observed. Next, rotate right through carry. That means your LSB moves to the carry bit moves to the MSB. So in this way, the logical representation is given here, and also one simple program being illustrated to understand how through carry the data moves to the MSB. So initially carry is assumed as 0. Similarly for RLC, that means rotate left through carry. That means the carry bit moves to the least significant bit or last significant bit. Then further shift happens. So in this way, this takes place. And one program is also neatly explained here. Kindly observe. Let's move to our second task, writing a program to find number of ones present and zeros present in an 8-bit data. So here, for this program, so each instruction is documented. I have written a comment for each instruction to understand in a better manner. So here, the first these four instruction, move instruction. So for initialization, what are we initializing? We have to first plan where are we going to store the number of ones counted, where are we going to store the number of zeros counted, and which register acts as a counter. So all this information I have to initially assume, and where the input is present, in which location it is present. So all this initialization part is taken care in this first four instruction. R1 does the job to store the number of ones. R2 is initialized initially 0 to store the number of zeros, to count the number of zeros. And 8 because 8-bit data. So for that 8 is moved here. And 30H is my original location where I have stored assumed the data 90H, 90H. And I am clearing the carry first because I am going to use RRC. So the initially carry should be made 0. Now content of R0 is this, 90H is moved to the accumulator. Now I am doing rotate right through carry accumulator operation to find out how many number of ones present and how many number of zeros present. So for the following instruction, the next immediate instruction is jump bit PSW.7, which is a carry bit. Instead of this, you can also use jump carry instruction. So this is another way of using jump carry. Jump bit PSW.7. PSW.7 is nothing but carry bit. So jump bit if carry is 1 to the label next. Next is mentioned here. So when in the LSB, if carry is present, if the data is 1 is present, immediately that shifts to the carry, and this instruction will find out whether the number LSB bit is 1 or 0. So in this way, if it is 1, immediately it jumps here and it counts the number of 1s. Every time increments whenever it encounters number of 1s present. So in this program you can see easily, you can track it. Number of 1s present are in this given data is 2, and the remaining data, there is 6 number of zeros are present, which will store in the R2 register, and R1 register will hold number of 1s is 2. The count, the increment happens twice, so the count becomes 2. So this particular instruction will do the counter decrementing and repeating this particular loop for the 8 times. So we can move every time, and we are going to check through the carry. The carry is present, then accordingly the respective registers will increment. Then finally, after decrementing till R3 becomes 0, it terminates. So this is the complete flow of this program. So it is well documented. You can easily understand. It's a self-study PPT. So next task is write a program to reverse a number. This program looks like having a very few instructions, but we have to understand thoroughly each iteration. So here the 8 is moved to the R0, which is a counter to rotate all the 8 bits, and the input data, assuming I have assumed some other data, AAS here. So assuming AAS here, and which is moved to the accumulator, and I am using rotate right through carry accumulator. So it does logically like this, and the accumulator is moved to the 30H. Again data is moved to the 30H, and 50H is a destination location. That means after complete iterations, all the iterations, so we'll find the result in this location, 50H location. Initially it is 0. Then I am using RLC here. So the RLC does the logical representation like this. So the carry is moved to the LSB. And finally, after all the 8 rotations, the result is stored in the 50H location. Let's find out how exactly it happens. So for that I have created one tabulation here. Initially, in the 30H location I have the data AA. The binary representation of that is this. Initially the carry is 0, and in the 50H location also carry is 0. So in the 50H location all the data is assumed to be 0, and this is my original data. So after reversing it, what happens completely? Let's go through each iteration. So in this program you can see, so the iteration 8 times it happens. So 8 iterations happen. So for each iteration, when I perform rotate right through carry and rotate left through carry, and we have to observe the 30H content and 50H content. So for that, this table serves that purpose. So we have to assume, we have to check in the 30H what is happening, in the 50H what is happening. So when I use the first instruction RRPA, the AA becomes 55H, and this 0 moves to the carry. You can observe the least significant bit moves to the carry, and this carry moves to the 0 here, the carry bit is here, and when this carry is moved to the LSB, this MSB comes to the carry. So accordingly the data will remain same because it's a 0 moves to this location, doesn't change, alter the original value. So accordingly the MSB here, the MSB is 0, that moves to the carry, and again this carry moves to the here to the carry. So for the next rotation, this carry bit moves to here, and this LSB moves to the carry bit. Please understand here, when I use this instruction, initially the carry is 0 here, so that moves to this MSB, and this LSB moves to the carry bit. So accordingly, so the data becomes 2A, and carry set, and this carry is moved to the next RLC operation. So when I use RLC instruction here, again this MSB becomes 0, and this carry moves to the LSB. Again this 0 moves to here, and for the next subsequent instruction you can identify how the iterations happen and how the data movement takes place, shift takes place for each instruction. So likewise, at the 8th iteration, your original content 30H becomes 00H, and your 50H will be holding the reversed value, reversed data, which is equivalently 66H. It is a completely reversed. Your 0 moved to here, and 1, your LSB moves to the MSB, your MSB moves to the LSB. So the result is this. So in this way, this program serves the purpose to reverse a number, and finally the result will be available in this location. So the last one, write a program to check the given number is a palindrome or not. So this set of program is from the reversing a number, the previous program. So the next one, again moving the original data to the accumulator and comparing with the original data and the destination, reversed data. If the data matches, after reversing also, when it is matching, then we immediately, what are we doing? We are doing is, so if the given data is palindrome, then move the content of 51H becomes 0. We are moving immediate value 0 to the 51, that signifies that it's a palindrome. If not, it moves here. If the number is not palindrome, if it is not matching, in the previous case also, the data A is being given, but the result is 66, which is not a palindrome data. This is a good example for which is not a palindrome data. So that means the 51H content becomes 01H. So in this way, the palindrome operation can be understood. Thanks for watching the video. Thank you.